Hello. In this video, I'm going to talk about chapter 22, electrostatic, and it's the first part of chapter 22. In this video, I'm going to talk about charges and general idea about electrostatic force. So gravitational force, normal force, friction force, tension force, these are the forces that we've dealt with. Now we're moving on to electrostatic force. Tension force, friction force, they're everywhere. You encounter all the time. Actually, electrostatic force too, that you see it in your daily life all the time. So electrostatic force, let's see, my kids helped me out for the demonstration, so I'll show you the video. Let's start with that. Share screen. Here. Here. Okay, so what do you have in front? What are those? The white things?
The tissue paper.
Tissue papers. Can you touch the tissue paper? Put another tissue paper. こうやって持ってもらえる? Yeah. Doesn't do anything, just a regular tissue paper. Alright, could you guys please tear those up? Smaller pieces. So it's just a regular ordinary tissue paper. Let me see. And then let me see. What I asked them to do was to tear up those tissue papers, of course. Let me see. Takes time. Here. They love tearing things up, so I asked them to do it, and they do a good job making it into small pieces. So it's the regular ordinary tissue paper, nothing special about that. And why don't I'll just show you. This is the failure video. It's not the one that's successful, but I'll just show you anyway. So I asked them to rub the balloons on their head. But my 3 years old boy, he's a little, he just didn't just rub the balloons. He did more than that. So I decided I'll take care. And so you see that tissue paper is just regular ordinary tissue paper. It's just nothing. It's neutral, right? And I am, by rubbing the balloon, and remember it's now warm. This demonstration works better in a colder time. We do have some humidity, so let me see. But now I took over and I did that. I am doing the work now. So here.
One action.
Rubbing. どう? Is it? Do you see my hair being stuck? Ichamo?
Yeah, it's starting to stick up.
Okay. All right, go closer.
Well, it's doing it. A little bit.
All right. So you see that after rubbing a balloon, if I didn't rub the balloon, I touched the tissue paper, it won't do anything. But the rubbed balloon touches the tissue paper, and then tissue paper was moving to be attracted. And that force to attract the tissue paper is electrostatic force. And source of electrostatic force is electric charges. Source of gravitational force is the mass. We did the Newton's universal law of gravitation, that you have anytime you have two masses, you have a gravitational force. Electric force, similarly, and anytime you have two charges, you're always going to have an electrostatic force. So the source of electrostatic force is charges. And then unlike gravitational force, which is the non-contact force, right? You saw the electrostatic force too. The balloon doesn't have to be in contact with the tissue. So electrostatic force is also, just like gravitational force, is non-contact force. So it's different from tension force, field force, tension force, friction force, and normal force. Their contact force, gravitational force, electrostatic force is a field force. You don't need to be in contact to feel the force. And you saw that tissue paper was attracted to the rubbed balloon. How about this? How about this? So now I'm going to rub both two balloons, not just one, right? Make sure and do a good job. You see what I do for you guys? Making my hair messy. And then see, I want you to see this thing. So here we have, I'm hanging the balloon, and this is already been rubbed, right? And then I have another balloon that's been rubbed too. So these two balloons are both rubbed, and then you see how they're both rubbed.
What happened?
Can you see the motion of yellow? When I put the blue balloon close by, what does it do? It doesn't want to be close to blue balloon. Goes away. Ooh.
Come on, my darling.
So you see that if I put the both balloons being rubbed against my hair, and then if I put the one balloon closer, the other balloon doesn't like it. It moves away. So they feel the force among each other, and this time the forces that's acting on them is repulsive, rather than tissue paper and a rubbed balloon was attractive. So this is repulsive force. So that's the difference between gravitational force. Gravitational force is always attractive to each other, but electrostatic force, it can be attractive or repulsive, and that depends on the combination of source, the electric charges. And we'll discuss more about this. So let's, we know that all the materials, all the matters are made of atoms, right? And atoms, inside an atom, we know that an atom has electrons, protons, neutrons. Inside the electrons and protons are, protons and neutrons are inside the nucleus, bounded tightly by the very strong force that's called nuclear force. Then around the nucleus, you have electron clouds. Neutrons has a mass, proton has a mass, electron have a mass, but neutrons does not have any electric charge. So you have a mass, but there's no electric charge. But proton, which is a similar mass as the neutron, do have electric charge, and we say that electric charge of the proton is positive. Electrons surrounding the nucleus have a smaller mass than the protons and neutrons, but it also has the electric charge that's same magnitude as the proton, but in this case, it's negative. So in the case of electric charges, unlike mass, we have two different polarities, plus and minus. Mass is just a mass, but electric charges has two polarities, plus and minus, right? Let's go into so let's see, I can show you the slide. Share here. So here, you guys already know this. I already, we talked about this. So inside the nucleus, you have a proton and neutrons. And see, you have a positive mark for the protons. That means it's electrically positively charged. Neutron doesn't have any electric charge. And then surrounding it is the electron clouds. That's negatively charged particle. So typically these atoms comes in electrically neutral. There's nothing, you have the number of proton is always the same as a number of electrons, and they both possess the same electric charge, which is here, same magnitude of electric charge. Electric charge for the proton is positive 1.6 times 10 to the minus 19. And then we have a unit that's called coulomb. This C here is coulomb, the unit for charge. It's like a mass, the unit for the mass is kilogram. Unit for charge is C, coulomb. I'm going to write to you. And then it could be either positive or negative, but it's a scalar, right? It's just to show the magnitude, how much charge it has. And the smallest unit of an atom, smallest unit of electric charge is from electrons and proton, and that's 1.6 times 10 to the minus 19 coulomb. That's the smallest unit of electric charge. And then depends on the proton or electron, it could be either positive or negative. It is the, so atom has a, because the atom has a positively charged in the middle, and then in the center, and then negatively charged electrons surrounding it. And when you have a two oppositely charged particles, then the electric force becomes attractive. But when you have a pair of electric charge that's same alike charges, either positive or negative, then the force becomes repulsive. So it's attractive, electrostatic force becomes attractive when you have unlike charges, plus and minus, minus and plus. And then when you have a plus or minus like charges, the electrostatic force becomes repulsive. Okay. So that it is the electric force that's binding these, making the shape of atoms, because you have a positively charged particles in the center and the negatively charged particle around it. That plus and minus, the attractive force, is binding an atomic atom. All right. But I mentioned that number of electrons come in the same. And then if that's the case, then how can we have if it's plus and minus same amount, then atom is electrically neutral. How can we have atoms can be charged? Then we learn about the ions, right? So here is sodium and two examples, sodium and chlorine. So sodium has an atomic number 11, which means that there are 11 numbers of protons in a nucleus. And that means that you also have an 11 number of electrons that sodium possesses. But because of you see in the periodic table too, the first shell of electrons can contain only 2 electrons. So 2 out of 11 sits in a most inner shell. And then the second shell of electron shell can contain up to 8 maximum. So now 8 out of 11 sits on the second shell. So there's going to be 8 plus 2, the 10 electrons are sitting in the first and second shell. Sodium has 11 electrons, so the leftover 1 is in the most outer shell. But this most outer shell has this availability for electrons, eight electrons to be able to sit in the most outer shell, but we only have a 1 that's left, that's sitting, and then 7 empty seats. So that's the sodium atom structure is like. So because there's only 1 that's sitting by himself for sodium, so it's just a lot easier for sodiums to remove that 1 electron that's in the most outer shell. So sodium atom has a tendency to lose 1 electron, and it becomes deficiency number of electrons. So you have a 1 less electrons compared to the number of protons, 11 protons inside nucleus. So that means that sodium tends to be positively charged because you have a more number of protons than electrons. So sodium atom has tendency to become plus sodium ion. Let's look at chlorine. Chlorine has atomic number 17, which means that 17 number of protons sitting in a nucleus. And you're going to have a 17 number of electrons too, same numbers, right? And again, the first shell fits 2 electrons, second shell fits 8 electrons. So 10 out of 17 electrons are on the first shell and the second shell. Then you have, because the total number of electrons for chlorine is 17, so 7 electrons are sitting on the most outer shell, which is on the third shell. And again, the third shell has a seats for 8 seats electrons, and 7 electrons are sitting on them. We have a 1 spot available, right? So in the case of a chlorine, to remove all the 7 electrons is a lot more work than just introducing 1 electrons into that 1 open seat. So chlorine has a tendency to obtain that 1 free electrons from somewhere and then put it in so that the shells are nicely packed. So chlorine has a tendency to have an excess number of electrons, and when you have a more number of electrons than a number of protons, then that atom becomes negatively ionized. So excess number of electrons means negatively charged ion. So you can see how the sodium chlorine is formed. Sodium has a 1 electrons, and then the chlorine has a 1 missing spot that it's better for them to share that 1 electron of sodium with the chlorine of the 1 available seats. So that's how the salts, you can see the salt can be formed in this way, NaCl. So you see that how the matter can be charged. It's just how the object or the balloon that you saw in a demonstration can be electrically charged is by sharing the electrons. It's not the protons, right? It's the electrons. So it's either the electron is either removed or introduced to the matter, then the matter can be charged. You have an excess number or deficiency of electrons, either positive or negative. So interestingly, it is the electrons. And we didn't know about that, electrons and protons, but we knew about the electrostatic force before we knew about the atomic structure. So physics was, all the physics is done by assuming that it's the positive thing. But then now we know that it is the electrons, the negative charge is the one that's doing the work. And then I also mentioned that we found out that most smallest unit of electric charge, electrons and protons, is 1.6 times 10 to the minus 19 coulomb. So it's a very, very slow and it's small, and then it has a rather strange number. It's not like a unit 1. It's a 1.6 times 10 to the minus 19 coulomb. And then this is all because that we found out about the atomic structure after we knew about the electrostatic force. So I mentioned that electrons or the electric charge is 1.6 times 10 to the minus 19 coulomb. When we talk about 1 coulomb then, so how much electrons do we have to have a 1 coulomb? It's 10 to the minus 19. 1 electron is 10 to the minus 19. So to have a 1 coulomb, you need to have about 10 to the 19 electrons, or here it says 6.25 times 10 to the 18 number of electrons to make up 1 coulomb. So when you hear 1 coulomb, that's a lot of electrons. A lot of electrons to have a 1 coulomb. 1 coulomb is actually very, very strong because you have so many electrons. And then, for example, lightning bolt is estimated to carry a charge of 10 coulomb. You know the lightning bolt is very powerful, and that's 10 coulomb. But you see that 10 coulomb means you have so much electrons. That's 10 to the 19, or it's about 10 to the 20 electrons. It's carrying number of electrons. And one more thing about the charges is that, so we say the smallest number, smallest unit is the electrons or protons, 1.6 times 10 to the minus 19. Can we have 2.5 electrons? We will never going to have a 2.5 electrons. It's just like, it's a, matter. You can't cut the matter into a half. So all the electric charges comes in multiplication of number of electrons or protons, right? So it's going to be either 1.6 times 10 to the minus 19 becomes, if you have 2 electrons, then this becomes 3.2 times 10 to the minus 19. If you have 3 electrons, you're going to have a 4.8 times 10 to the minus 19. You can't have a 2.0 times 10 to the minus 19. You can't, because you cannot have 1.4 electrons. You're always going to have 1 electron, 2 electrons, 3 electrons. So this electric charge is actually quantized. It's not a value. Electric charge cannot be gradual. It has to be quantized because it depends on the number of electrons, excess or deficiency of electrons. But because the amount is so small, right? It's 1.6 times 10 to the minus 19. And then you're dealing with so many number of electrons typically that it almost looks like those steps, the quantization steps, seems very, very tiny that it almost feels like a smooth curve. So it almost seems like it's a gradual, but it's actually quantized because you can have half electrons or 1.3 electrons. Hope that explains. So then go back to this slide again. If the object has a net charge of 8.0 times 10 to the minus 19 coulomb, what is the net charge? How many electrons did this object lose? 8.0 times 10 to the minus 19. So this object has a net charge of 8.0 times 10 to the minus 19. To find the number of electrons, you're going to divide this by the electric charge. So 8.0 times 10 to the minus 19 divided by the 1.6, 10 to the minus 19 is 5. So this one has the 5 electrons removed. So you can see that if it's 1 electrons is removed or added, then you're going to have a 1.6 times 10 to the minus 19 is missing here. And then 2 electrons, 3.2, 3, 4, 5 becomes 8.0 times 10 to the minus 19. So it's going to be quantized. Again, the electrostatic force is a non-contact force, just like a gravitational force. But unlike the gravitational force, the source of electrostatic force can be has two polarities, positive or negative. So when you have unlike charges, plus and minus, the electrostatic force becomes attractive. And then when you have a like charges, it becomes repulsive. So if you have a minus and minus, it becomes repulsive. If you have a positive and positive, it becomes repulsive. So I hope you see that demonstration a little bit better. When I had two balloons and then I rubbed it against my hair, both of them are charged, right? And then it's the same material, the balloons. So they're, I forget the balloon is negatively charged or positively charged, but you have the same similarly charged balloon. And then because they're both the same sign, when I bring the blue one close by, yellow balloon doesn't feels the repulsive force, electric force, and it moves away. That's what that demonstration was doing. So two balloons, they're both charged similarly, and then you saw the repulsive electrostatic force. Let me write it onto the whiteboard. So we're in chapter 22. Green, sorry. Which is about electrostatic. So electrostatic. If we were in a class, I usually have a glass and a plastic, and then I rub it against the material. So for example, if I had a plastic bar, so I think the balloon is like that too. If I use the silk to rub it, then the positive, the plastic becomes negatively charged. Versus if I have a glass and then I have a fur to rub, then the glass has a tendency to be positive. So it depends on the material, like you saw the sodium and chlorine. Some of them has a tendency to be positive. Some of them has tendency to be negative. And what I'm doing, actually, we're going to talk more about this, but it's just simply the friction. Just applying some friction on a material, rub it against each other. We're just ripping off or introducing electrons onto the object. It's a very simple thing that it's just electrons are so easy to be removed or added. And also electrostatic force is so large. Remember, just having the one, the lightning contains 10 coulomb. And that's so much electrons. And then lightning is powerful. So you don't need to have a lightning like electrostatic force. So you don't need to have too many electrons to feel the electrostatic force. And I'm going to talk about that more about it. Okay, so source of electric. You see that source. Electrostatic force is the electric charge. And then for electric charge, I typically use Q. So mass, I use M. Electric charge, I use Q. And again, this is a scalar. And the unit we use is a coulomb. How much charge it is, just like a mass, kilograms for the mass, use coulomb, C. Okay. And this has two polarities. It could be either positively charged or negatively charged. Either you have a excess electrons or deficiency of electrons. And smallest unit of electric charge is 1.6 times 10 to the minus 19 coulomb, either positive or negative. So that's the smallest unit, and then it's quantized. And electric force. So to have an electric force, you need to have charges. And if you have like charges, just like positive and positive, or negative and negative, then the force becomes repulsive. But if you have unlike charges, that means you have a combination of positive and negative, then the force becomes attractive. So depends on the combination of charges. Again, Newton's third law says that you need to have two objects to have a force. Force always come in pair. And that two objects, in this case, the source of electric force is the charges. If it depends on the combination of the charges, you could either have a repulsive force or attractive force. And just like a gravitational force, electric force is non-contact force. As you saw that tissue paper, you don't have to touch the balloon to attract the tissue paper. Or you don't have to, I didn't have to touch the blue balloon to repel the yellow balloon. They don't need to be in contact because the electric force is non-contact force. So it's similar to gravitational force. All right. Yeah, so this is the introduction for electrostatic force, chapter 22. And then we're going to discuss more in detail about the electrostatic force, and then field. We're going to talk about how can we more about charging, and then what kind of electric materials out there, and then electric field and electric potential. But I'll see you in the next video.